In this video, I will explain the concept of deep transfer learning. This picture, in a way, represents or summarizes the idea here. Say, for example, my model, my source model, which has some pre-trained knowledge in it. And then here's my new model. And what we would like to do is transfer the knowledge that this pre-trained model already has. So this is a model that is already trained to a new model that we are training. So we'll start by discussing how we can use a pre-trained convolutional neural network, or ConvNet. Now, a pre-trained network is a saved network that was previously trained on some large data set, typically on a large-scale image classification task. And this is typically using data sets like ImageNet on very large networks. So we'll look more into this. If we train a network on, say, for example, the ImageNet data set, once we finish the training, we can repurpose this trained network. Let's say we build a model M1 from the ImageNet data set, then we can repurpose this model M1 for something else. So even though it may be trained to predict, let's say, for example, the 1,000 classes, this model can be used to do other things. What's very interesting is sometimes these models can be used to do things that are even as remote as identifying furniture items in images. So a network trained on ImageNet can be used to later repurpose to predict, let's say, chairs, tables, various kinds of furniture items. And some groups, some research papers discuss applying these pre-trained networks to medical imaging, pictures taken by regular cameras as well, which is quite different. So the data sets the medical imaging data sets and all those data sets are very different from ImageNet, which, say, for example, was used to train this model M1. But even if problems are very remotely different from the original, the model that was used to train a different data set, these models can be useful. And this is mainly because of the portability of learned features across different problems. In other words, even though the image data sets, let's say, for example, this is my ImageNet data set, and let's say I have another data set, medical imaging data set. Let's say this is another data set that we have. Both of these data sets, even though they are completely different pictures, many of the core features of these images can be same. So core features of these two pictures can be same. And that's where this pre-training or using a pre-trained model seems to be helpful. And the way this works is, if we say, for example, take this ImageNet data set and build a really deep model, let's say deep model, then what happens is the earlier parts of the model learn some very basic things that can be applied to other problems as well. And this is what makes deep learning different from other shallow learning approaches. Now, using a pre-trained network or a pre-trained model trained on large data sets can be done in two ways. One is using a technique known as feature extraction, and the second is using a technique known as fine-tuning. And remember, for example, if we pre-train a model or train a model for pre-training using the ImageNet data set, then this is 14 million images with classes, mostly animals and everyday objects. So if we train a model using this ImageNet data set, then the model has a lot of ideas about how the real world looks like. So going back to the two ways to use a pre-trained network, we have one way is feature extraction, which is a more practical and a more common and less resource intensive way of using pre-trained networks. And the second is fine-tuning. We'll look into both of these one by one. Now let's look at the first technique of using feature extraction. Now, feature extraction is taking the convolutional base. Now, we'll look into what this convolutional base is. You're taking the convolutional base of a previously trained network and running the data through it, and then training a new classifier on top of the output. Now, to look at this visually, let's say this is our model pre-trained. So this is our model, let's say, pre-trained on really large data set, let's say ImageNet. So this is pre-trained on ImageNet, let's say. So if this model is pre-trained, then we can see the model as having two parts. One part is, so here's the input, just to summarize, and then this goes through. So this is slightly in a different perspective. Usually the input is represented on this side, and here's your model, this is your input, and usually there's output on this side. But in this picture, we have the input at the bottom, and this input goes up to the trained convolutional base. So this is the, if this was, say, for example, VGG16, then this part represents the CNN region of the VGG16, and then this part represents the dense region. So this is the trained classifier, and this is the trained convolutional base. And here's the prediction made by the dense layer at the end. Usually we will have 1,000 neurons at the end to predict the actual classes. So the way feature extraction works is that what we simply do is we take this model, we take it as input, and then we remove the classifier. So this part, that is these dense layers, we ignore them. But we simply keep the convolutional layers of this pre-trained model, and also their weights. So remember, these are pre-trained weights. So pre-trained, we have the weights here. Weights are already here. So we keep them, and then what we simply do is, in the next step, we attach a new classifier. That is, we have a new dense layer. And then what we simply do is we still pass the input through this model, but the weights in this network, weights in this CNN part, weights are frozen. What this basically means is our input passes through these convolutional layers, which do not change their weight during training, but then this dense part of the network, that is, let's say, dense 1,000 layers or however many layers we have, all of those are randomly initialized, and then this is the part that gets learned. So this dense layer is the part that learns, or the weights are learned during the model training process, or during the model.fit process. Now, going back to the topic, one may ask this question: so why skip the dense layers? Now, what researchers have observed is that the representations learned by the convolutional base are more generic and therefore more reusable. So what people found is that this part of the network, that is the CNN part of the network, in a way learns the general things about images in the real world, and then the top part, the classifier part, or the dense part, learns more specific things about the problem. So even if we ignore the dense part, what the convolutional base gives us is a different representation of the input, where features are extracted into a different dimensions about the from the input images. So it doesn't actually do the classification, but what it does is converts the input to a format that can be now more easily classified. Now, the next technique is fine-tuning. Now, in fine-tuning, what we do is we even change some of the, we even let some of the convolutional layers learn new weights. So what we can do is actually, say for example, we have a network that looks like this, and the blue region, all this blue region and this yellow region is a pre-trained model. And let's say we have this our own dense layer, for which we need to learn the weights. Now, during training in Keras, in TensorFlow, what we can do is we can select certain layers and we can freeze the weights of those layers during training. So I can select this convolutional block 1 and then make all the weights of this convolutional layer frozen. What this means is during training, everything else will change, but the weights of these convolutional layers will not change. Similarly, I can keep the convolutional next block also frozen. All the weights will be frozen. Block 3, block 4. And then what we do is some of the convolutional layers, say 3, 4, 5, or even 2, or even 1 convolutional layer that is closer to the dense layer, we can keep them unfrozen such that we can fine-tune these convolutional layers as well. So in a way, the initial layers, these initial layers of representation, so initial layers, the representations learned by these initial layers are kept constant, but then the representations learned by these later layers, we let them change, we let them evolve. So we don't initialize them to random, we let them the weights, whatever it was after the pre-training, but then we let the weights update so that it's more effective on a new problem as well. So fine-tuning basically means unfreezing a few of the top layers of a frozen model base used for feature extraction. Now, once we have this setting, what we simply do is we jointly train both. That is the newly added top part of the model, that is this green part, that is the dense layer, and then also these top layers. That is the top layers, the convolutional top layers for which we have unfrozen the weights. Now, why is it called fine-tuning? So this approach is called fine-tuning because we slightly adjust the more abstract representations of the model being reused in order to make them more relevant for the problem at hand. Now let's talk about an example. So say I have the ImageNet dataset, and then let's say I have a VGG16 model that is trained using ImageNet. So this becomes my pre-trained model, right? And then the problem at hand I have, let's say, is cat type, let's say, classification, right? So we have many kinds of cats, and we would like to create a model, build a model that can classify various kinds of cats. Now, obviously, what we will do, we know that a VGG16 pre-trained model will be helpful. So we take this VGG16, we keep the top part of VGG16 as it is, and then we attach a new dense layer, new dense module, or even we let some of the layers in the VGG16 unfrozen so that we can update the weights. And then now on this new model where these weights, all of these weights are previously learned weights, and then these are random weights, right, in our model. And then we train these on our new cat dataset. So then the model doesn't start from the scratch, but it already starts from these pre-trained weights. But these weights are random, but the remaining part is already pre-learned. And then we keep training it for certain epochs, and then later we should see a much better improvement compared to training a similar model from the scratch. So if we are doing fine-tuning, here are the steps involved. The first step is to add your custom network on top of an already trained base network. So if this is the VGG CNN part, let's say VGG CNN part, then you attach your dense layer on top of this, right? Then we freeze the base network. So we freeze this network, and then train the part we added. So we train these dense layers, train these dense layers, and then we unfreeze some layers in the base network. So then we select some of the layers we want to relearn, let's say the last 2-3 layers, and then we unfreeze them. So we unfreeze them after that, and then jointly train both of these layers and the party variable. So then after that, we keep these frozen, keep these initial layers frozen, but then leave this some of the end of the base and our new part unfrozen, and then we train the whole network. So this is how fine-tuning should be done, because if we don't do this and simply unfreeze the base layer at the beginning, then the model may have a harder time learning, because instead of learning first the dense layer, it may start changing updating the weights of your convolutional base as well at the beginning, which may make the training, which may make you wait longer to obtain the results. Now, fine-tuning is not an easy way to do transfer learning. And a more common and the easier way to do transfer learning is the first technique, that is the technique of feature extraction. Now, you may have noticed that in the technique of feature extraction, what we simply do here is we have a frozen part of the network, right? This is the CNN base, right, that delivers your representation, let's say in some format, and then this gets fed into your dense layer, right, and then it's where we get the output. Here's our input, and this passes through the CNN base, which is frozen, and then passes through the dense layer, which is later learned, right, and so on. Now, because this CNN base is very heavy, a very smart idea to get around the training of this really large network is to do this. That is, we take the input and we say we take all the input images that we have, pass it through the convolutional base, obtain these representations, and then save these representations into files or somewhere in memory. Then after that, we never have to worry about these part during training. We can simply create your input X from all of these data sets, pass them through the network, build a neural network model only for the dense part, train this model, make it work, and once things work out, for your final prediction, say you have a new input image, then what you simply do is pass the input image through the CNN base, obtain the representation, and then pass this representation to the model that you trained to obtain the output.